Right, our next speaker is Deovrat, who's going to tell us about cold gas and AGN feedback in galaxy clusters.
Hi, everyone. I'm Deovrat, and I work with Pratik, and this work is basically done in collaboration with Arif at University of Victoria. So as our previous speaker has already explained what the cooling flow problem is, and AGN Jets were proposed as the heating mechanism for controlling this catastrophic cooling flow in cluster cores. Now, although more or less people are agreeing on the point that AGNs can be the possible heating source, but the details of it is not very clear as to how the coupling of AGNs will happen with the intracluster medium. Okay. So the proposal is like this, that the feedback cycle will start when you have a dense core, and if you have a dense core, that will lead to a very fast cooling rate or condensation as cooling rate goes as n square. Now, once this condensation starts, it will lead to formation of multiphase medium. You will have cold gas clumps condensing out of the hot ICM. And these infall of these cold gas clumps, it will lose the pressure support and fall towards the center of the cluster. And these falling cold gas clumps will fuel the AGN, and which will in turn heat the cluster cores, and which will bring down the accretion rate, and which in turn will lead to a low jet power, and the cooling process will start again. In our simulation, what we have done is we have tried to model this scheme in 3D. Okay, so this is our schematic. We have used these source terms basically is used to put the jets in the active domain, and the jets are basically put at around 1 kiloparsec to 2 kiloparsec region with a confined half angle of 30 degree, and the jet mass loading factor is calculated using this equation where epsilon is a free parameter which takes into account two things. One, the amount of gas that, let me first tell you the m dot accretion, then that will make more sense. So we calculate the m dot accretion as all the gas that crosses the inner radial boundary, and our inner radial boundary is at around at 1 kiloparsec. So this epsilon parameter takes into account two things. One, the amount of gas that will cross the 1 kiloparsec region, and that will ultimately go to the black hole. And second, the amount of gas that feeds the black hole will get converted into the kinetic energy. So this parameter has to be really small. A lot of simulations which were done before we started this had this epsilon parameter as like very high, which was sort of not physical. So also we fix our V jet at 0.1 c at the base. So this is how our initial setup looks like. We seed this the density. This is the density snapshot. So we seed our density with a small density perturbation to start the multiphase cooling. Our resolution is really good in the sense that they're like the near the core, the grid size is of the tens of parsecs. So this is really nice, and our epsilon parameter is really small because that is what is physically possible. These are different density snapshots of our simulation, and this is done over like a cosmological time scale. So, so these are different phases of our simulation, showing jet activities and rising bubbles. If you concentrate on this part, as in the next slide, you will see that these cold gas clumps are condensing out in blobs and falling towards the center. So the accretion process is not like a continuous process. It's more of an episodic in nature. So as cold gas clumps fall into the center, it will give rise to a strong jet, and which will kind of disrupt the whole thing. If you look at the pressure maps of these AGN cavities, you will see that you have a very distinct contrast between the AGN cavity and the ICM. But if you look at the pressure maps, they're mostly in pressure equilibrium. So this more or less asserts the point that these cavities are rising buoyantly in the ICM. Okay, this map you have already seen in the previous talk, but this basically shows you like these cavities here. So I don't go to. Okay, so the other thing that we found in our simulation was we started with a setup where we didn't have any V-phi, and we ran this simulation. So this is just a hydro simulation, no magnetic field in it. And as the system evolved, they initially had a very stochastic kind of angular momentum because they gained it from the turbulence and all the mixing happening at the core. As the system evolved, this initially they were in counterclockwise, then they become clockwise, and as the system evolved, they settled down into one sense of rotation. And this cold gas torus is very dynamical in the nature because they kind of break apart whenever there is a strong jet activity, and they reform again, and this keeps on happening throughout the lifetime of ours, throughout our simulation time. This is an observation of in Hydra A, where they observe this rotating torus at the center, and this is roughly around 3 kiloparsec, which is the scale which we get the torus. And what it basically says is like this is a BCG Hydra A in Hydra cluster, and what it says is like these tori are like more common than what people expected. Okay, now let's look at the jet power and what effect does it have on these cold gas clumps. So this is a plot of jet power with time, and this is 10 to the power 41, so this would be like 10 to the power 43, 44, 45. So if you look at the episodes of, if you look at the inflow and outflow of the gas at roughly around say 5 kiloparsec, what you will see is this is an outflow map, and every jet event that you see coincides with a very large outflow. Almost every one of them. And if you look at the inflow at 5 kiloparsec, these are cold gas, by the way. Like the dormant phases coincides with like a very strong inflow, like these condensation phases. If you map, if you bend the mass as a function of velocity and radius, this is radial velocity, you will see a very distinct kind of mapping. What during the outflow phase around this point, you see a very strong outflow component, while when there is a very strong inflow here, you see an inflow component. The major distinction between these two is this fast component is absent in the inflow phase. So this fast component is absent in the inflow phase. This was another observation in Abel 1664. What it shows is two distinct cold gas, molecular cold gas clumps. This has a velocity of about 500 to 700 kilometers per second, while this goes from minus 200 to plus 200 kilometers per second. So this basically, what we are thinking is this is basically a disk component or an inflow, while this is definitely an outflow component. So that is more or less what I had to say today. Thank you. So our conclusion is like cold mode feedback controls the catastrophic cooling flow in clusters. By the way, we were able to get cooling flow control up to like 1/10 of the pure cooling flow value. Like if you just had cooling, no heating, and if you had these AGN jets with our efficiency, this would bring down the m dot accretion to 1/10 of the original value. So the original value which we ran for our simulation was 250 solar mass a year. These brought down them to 24. So a higher efficiency will give you a better control. One of the major problems with the simulations which were done before us was they had a very high accretion efficiency, and because of that they were overheating the whole system. And that's why you had this Lee paper, which Lee et al.'s paper, where you had this torus formation, and the torus would be like present throughout the lifetime, but there would be no cold gas, extended cold gas. So the decoupled nature of the cold gas is basically shown over here, that the tori which is present there is basically decoupled from the whole feedback process. You have this extended cold gas which is falling, will basically control the feedback cycle, and the tori which is there would basically dissipate with the star formation and stuff. And that is all that I have to say. Thank you.
Right, time for one quick question. Robert's hand went up first.
I'd like to know a little bit more about the physical parameters of what you call the torus. I mean, for a start, is it thin or is it thick? What's its temperature?
These are all cold gas. So like these are gases with temperature less than 5 × 10⁴ Kelvin. So.
I mean, the motivation is that we see very often disks of very cold gas,
so
CO and dust, in radio galaxies. They're quite thin. They can have masses of up to 10⁹ solar masses in molecular gas. Are these the things that you're talking about?
There is one slide. Okay. Yeah, you'll see this component. This is the tori component, and this is roughly 1 kiloparsec. So you can imagine.
So it's about a 2:1 aspect ratio on average.
Yeah.
Okay. We need to move on. So let's thank the speaker again.